Sublimation. So sublimation is the transition directly from the solid to the gas state. It's kind of unusual. But if we think about a block of ice, the molecules in a block of ice have thermal energy. They're vibrating around a fixed point. Some have higher energy, some have lower energy. If you have molecules at the surface with high energy, they can break loose from their neighbors and go into the gas state. That's called sublimation, going from a solid directly to a gas. The opposite is called deposition, going from a gas directly to a solid without making a liquid in between. So solid water, ice, also has a vapor pressure because there will be a bit of water vapor in equilibrium with the solid. It's just going to be very, very small. Sublimation is going to happen at a greater rate in an open container because then the molecules that escape into the gas state leave, right? And they don't come back and they don't get condensed. This explains why ice cubes that are left in the freezer will slowly shrink. Find some ice cubes, an ice cube tray in the back, or maybe some ice cubes in the ice maker. They got stuck up in the corner and didn't get used. And they're smaller than the fresh ice cubes. Somebody going in there and shrinking your ice cubes? No. The ice is sublimating. It's going into the gas state. This explains why ice crystals grow inside airtight bags of food. You get a bag of tater tots, right? And you forgot you had it, and so it's been in the freezer for a while, and you, oh, good, I'm going to have tater tots. And you dump it out in the pan, there's all this ice crystals. Why the heck do they put ice crystals in with the tater tots? You stick it in the oven, and it melts, and it gets everything all soggy. What would they do that for? They didn't do that. When it was fresh, there were no ice crystals. That water was in the tater tots. As the tater tot sat in your freezer, the ice sublimated and went into the gas state. Now, the bag was sealed, and so the water couldn't go away, but it's not going to go back where it came from. It's just going to run into something, and it's going to condense and make ice crystals. This is why foods get freezer burn and become dehydrated. I think all of us are old enough that we recognize when you put something in the freezer, you don't just put a steak in the freezer, right? You wrap it up in something. Little kids are so funny. We'll save that sandwich for later, and they just stick it in the refrigerator on the plate. You have to tell them these things. But even if you wrap your food, it can still get dehydrated. We call it freezer burn. It's called hard and nasty because the water can sublimate and come out of the food. The tighter you wrap the food, the better it will last, because if there's no airspace for the water to go anywhere, then it won't. And if you use a deep freeze, the colder the temperature, the less sublimation will happen. Dry ice is a very cool substance. I guess that was a pun, but I didn't mean it to be. It's solid carbon dioxide. It sublimes at room temperature, but it doesn't melt. That's why they call it dry ice. It's like ice, it keeps your food cold. But regular ice, I guess you could call wet ice because it melts and gets everything soggy. Dry ice doesn't melt, it just goes directly to the gas state. Any questions about sublimation? Fusion is melting. As the temperature of, say, the block of ice increases, the molecules vibrate faster. And at the melting point, the molecules have enough thermal energy to overcome their intermolecular forces enough that they can slide around and become a liquid. So melting and fusion are referring to the same thing. That's going from a solid to a liquid. Freezing is going from a liquid to a solid. Now, here's an interesting question. What's the opposite of melting? Freezing. There's a multiple choice question I like to give sometimes. I think it was, what's the opposite of freezing? And the choices were boiling, evaporation, sublimation, deposition. I gave this to my 3A class last summer. All but one of them chose boiling as the opposite of freezing, because the correct choice was none of the above. Boiling is not the opposite of freezing. Melting is the opposite of freezing. Okay? We see a similar heating curve for melting that we did with boiling. If you take the ice minus 10 degrees and you heat it up, the temperature goes up until you get to 0, and then it begins to melt. And as it melts, all the heat that's added in here goes to breaking intermolecular forces and turning from solid to liquid. And so the temperature remains the same until all the water has melted, and then the temperature goes up again. This is very convenient because if you want to establish a temperature for something, you can establish 0 degrees Celsius very easily. You make an ice water bath and you stick the thing in there. Don't need a thermometer, it's 0. And it's going to stay 0 as long as you've got ice and water present.
So if I have a big hot molten metal, when it solidifies, is that freezing?
Yes.
Yeah?
Yeah. Yeah, you can melt metals. It's not easy, but you can do it. Yeah. And then when it solidifies, it freezes. And the properties of the metal that you get are going to depend on how it cooled.
Okay.
Yeah. So if the metal freezes too quickly or it freezes very slowly, it's going to have a different crystal structure, and so you can have different properties. It happens with chocolate too. So there's energy involved in melting and freezing. I think we naturally understand that melting is an endothermic process. You think, well, how do I melt a block of ice? I need to heat it up. I put heat into it, it will melt. How much heat do you need? It's the heat of fusion. So fusion and melting, we typically use the word fusion, and that just doesn't really mean much to students. The way I rationalize it is, if you're melting chocolate chips, as you heat them and they melt, they fuse together. That's how I remember it. Fusion is melting. So we could look at H2O solid to liquid, and the heat of fusion is 6.02 kilojoules per mole. Melting's endothermic, freezing is exothermic. Heat is released. I live in Reedley, where we've got, it's the fruit basket of the world, a claim. Not the raisin capital of the world, that's Selma, but fruit basket. We've got a lot of orange trees, and in the winter, when the temperatures drop down, the oranges are in danger of freezing. Oranges freeze, your crops ruin, it's just terrible. So how do you keep the oranges warm? You flood the field. You water the field, get it really good and wet, and then it helps to have the wind machines to stir the air around. But in that field, where there's standing water on the ground, as the temperature drops, the water begins to freeze, but the temperature of the water freezing doesn't go below 0 degrees Celsius until all the water has frozen. And so it keeps the temperature of the air around it warmer, because as it freezes, it releases energy into the air. And so, this would not allow you to grow oranges in Minnesota, but if you're wanting to fend off freezing when it's like 26 degrees Fahrenheit and you want your oranges to not freeze, you can do that just by getting the field good and wet. It's kind of neat how chemistry saves orange juice. Heat of fusion is generally a lot smaller than heat of vaporization, because when you're melting something, you don't have to completely overcome the intermolecular forces. You only have to partially overcome them. You just have to get loose enough that you can slide around. You don't have to break free completely. So here's a graph that shows the difference. There's heat of fusion, heat of vaporization. Takes a lot more energy to vaporize. And then there's some heats of fusion for some substances that you might find useful for a homework problem.